Hi everyone and welcome to the Multi-Scale Modeling Workshop. My name is Gabriel Krenzer and I'm a second year Faraday Institution PhD student at Imperial College London. My supervisor is Professor Aaron Walsh, and today I'm going to talk about phonon-ion interactions and how we can use lattice dynamics to improve the design of solid-state electrolyte for next-generation solid-state battery applications. In a liquid battery, we use a liquid electrolyte, and that's where the ions are channeling from one electrode to another. And this is an essential part to the overall functioning of the battery. In a solid battery, what we want to do is to remove the flammable liquid electrolyte to replace it by a solid electrolyte to make an inherently safe battery. Other advantages include increased energy density, increased lifetime, as well as increased temperature resilience to extreme temperatures. And to understand a bit more what's required to enable that shift from liquid to solid, we have to zoom in at the electrolyte level because that's where the chemistry is changing. And I'm interested in diffusion processes, and I've pictured here the different diffusion processes you can see in liquid and in solid. In a liquid, you apply the voltage, and the pink ions, for instance, is channeling from one electrode to another, and all the surrounding ions are moving together with it. And therefore, there's almost no resistance to diffusion for that pink ion, hence the flat potential energy surface. On the other hand, in the solid electrolyte, the surrounding ions are static, and therefore the pink ion has to go in very energically unfavorable places, hence the activation energy barrier and the overall sinusoidal shaped potential energy surface. In a bit more details, what happens is that the pink ion is vibrating at a frequency gamma, which is the attempt frequency to go over the activation energy barrier. And this gamma has been shown to be the average vibrational frequency of the diffusion species according to a high-throughput study on a wide variety of compounds. So these two potential energy surfaces suggest that we need to look out for faster for solid electrolyte that conduct ion in a quicker way, because they can't compete with the liquid electrolyte, and that involves materials discovery. And in particular, I'm interested in a class of compound called superionic conductors. And so I've chosen copper chromium selenide to illustrate that. So in the normal state, you can see copper chromium selenide. Each atom is in its atomic state, and there is crystalline periodic order. Copper ions, which are diffusing in the AB plane, are diffusing by vibrating and hopping, just like the solid we've seen earlier. On the other hand, in the superionic regime, you can see that the copper ions are first much more delocalized. This is specific to the diffusion species. Chromium and selenium are still located at the atomic site, so this is a sublattice melting. But more importantly, copper has been identified as diffusing in the AB plane. So there's a transition of vibration to diffusion, and therefore from normal state to superionic. And so we have a liquid behavior within the solid, because this is the ideal compound for a solid state battery. And so what they did in this study is they monitored the vibration properties of this 8 milli-electron volt mode, which corresponds to copper, and monitored it across the superionic transition. For reference, they also monitored this acoustic mode, which doesn't change much as we increase temperature. Going into the details of what they observe is a decrease in fitted energy for this 8 milli-electron volt mode, which is proportional to frequency. And so there's a decrease in frequency, but in fact, this gamma is proportional to the square root of the activation energy barrier. So there's the flattening of the potential energy surface as we go closer to the superionic transition. But most importantly, what we observe is a drastic increase in the peak width, which is inversely proportional to the lifetime of the mode, and therefore there's almost an instantaneous decay of the vibrations. And therefore, in this paper, they identified it as a passover of the vibrational degrees of freedom to diffusion. To understand a little bit better what's happening, we can go from classical to quantum and think about vibrational energy levels. And so we start in the ground state with a given activation energy barrier. As we increase the temperature, we go in a higher excited state and lower the activation energy barrier. We're still vibrating here. But then we go over the superionic transition temperature, and we access to an excited state that is leveled with the activation energy barrier. And there's no felt activation energy barrier for that copper ion, and it's simply diffusing through the lattice. And so we go from vibration to diffusion, from normal to superionic, and in this case, we have the ideal compound. So we set to explore that a little bit more in lithium-ion conductors, and so we chose to look at lithium nitride because it has a decent ionic conductivity. It's also very, very simple to model, so very easy to carry out computational calculations on that compound, and it also shows signs of a superionic transition. So the lithium ions are mostly diffusing in that lithium nitride layer, and so what we want to calculate are the evolution of frequency with respect to temperature, the evolution of lifetime with respect to temperature, and also the density of states. Okay, so to calculate that, we need to go to lattice dynamics theory, and so this is a Taylor expansion of the potential energy. So the first two terms are not very important for our purpose, but the second order terms can give us a bit of information, even though the harmonic term, the so-called harmonic term, does not include in the description of temperature. But in fact, what we can do is to calculate harmonic terms at different volumes within the quasi-harmonic approximation and get the frequency shift with respect to volume expansion. The third order term can give us the lifetime, while the fourth order term can give us the intrinsic contribution to frequency shift, so more quantitative effects contributing to this frequency shift. So the first part of my PhD was to compute this and calculate the frequency shift with respect to volume effects. So this I have done with Phonon-ion, which I've referenced at the bottom, and you can also find the link to a repository which can help you getting started with phonon calculations. And so you can see in that phonon dispersion, first the dark green lines all corresponds to the 0 Kelvin phonon dispersion, and then the lines with different shades of green and blue corresponds to different temperature ranging from 0 Kelvin to 700 Kelvin. So you can see here and here, you can see softening, so decrease in frequency as we increase the temperature. But to understand that a little bit better, we need to go to this equation and see, which vibrational modes are mostly contributing to this gamma, which is proportional to the square root of the activation energy barrier. So we need to look for the highest peak, the largest peaks in the density of state. So that's what we do. And then we project that on the phonon dispersion, and we identify here 3 modes, and then another one here that's softening. So we can see a lot of softening there. And in fact, when we project the eigenvectors, so to identify how the ions are vibrating there, we can see that we find 2 in the plane, and then this one as well is in the diffusion plane. So we identify those 3 modes as the most interesting one and the most likely to actually contribute to the overall diffusion mechanism seen in lithium nitride. In the future, to further prove that fact, we want to use molecular dynamics simulation to identify the diffusion mechanism, plot the energetics of that diffusion mechanism, and then project the energetics of those 3 phonon modes onto the diffusion mechanism and see if we can replicate it. Also, with molecular dynamics, what we can do is use the software DynaFoPy to interpret the molecular dynamics data, which can then give us the lifetimes, the intrinsic contribution to frequency shift, and the density of state. So with that, we would be able to complete our study. The problem with molecular dynamics is that we usually compute our forces using density functional theory, which is very expensive. In fact, I've run this for 172 hours, for 100 picoseconds and 256 atoms. This is much cheaper in SNAP potential, which are machine-learned interatomic potential, which we have been designing with collaborators. And you can see that the problem is that if you start scaling higher and higher, DFT is just not feasible, whereas SNAP is actually doable. And so we benchmarked our SNAP potential with respect to DFT because we're interested in phonon properties. We compared phonon dispersion and got a very good agreement. So in the future, we want to use that SNAP potential to compute the last properties we need to compute to further investigate the origin of superionic transition in lithium nitride. And with that, I'd like to thank all the people that have been involved on that project, the computational resources I've been lucky to use, and you can find my email address at the bottom here. And with that, I'd like to thank you for listening, and I'll see you on the 28th of April for a Q&A panel.